Hello everybody, this is just a quick little demonstration of today's entry. It's an emergency contingency human ventilator push release type bedridden ventilator. Alright, based on, I haven't really done much research on it other than that it makes sense that I know that a lot of PPAP or CPAP ventilators for people who have sleep apnea are basically positive pressure, which means it's a fan that just constantly blows. It doesn't change speeds or whatever. This base starts from that and basically uses a similar blower, although I've used a higher volume blower. I'm using one that's 65 cubic feet per minute, so that's more than enough that I would never need for a human. And I haven't built this yet. The parts are mostly on order. I already had the Arduino Uno R3 and the power supply, and so I'm ordering the blower, the mask, the hoses, and potentiometers. I can get those anywhere. I have a power cord for that. So the whole cost is about $134. It'll vary, between people. So let's just go over the basic functions of it. This is a PC power supply that you'd probably pull out of an old desktop computer, which is what I do. I never throw anything away, so I pulled out a power supply. And what you have to know about these little power supplies that you pull out, they're about this big, about 8 inches square or cubed. And they're pretty good. They got like different voltages, plus 12, minus 12, plus 5, plus 3.3, minus 5, standby voltage, things like that. And they're pretty up in the high current. The one I have has a 14 amp, 12 volt DC, so you need at least 7 amps for this circuit or this design. And what you have to know is that some of the power supplies will not power up unless you load the 5 volts. So you need about a 5 ohm, 5 watt minimum, but you should always have more wattage on your resistor than the maximum. So you need a 5 ohm resistor on the 5 volts, and of course you have to tie the green wire to ground, which is the switch, the power on switch, the electrical switch. Basically turns on the supply. The standby voltage, which is 5 volts, is always on, but there's very low current. So anyway, you could probably get these from surplus. You could probably even buy these new, but it'll be more than $10, I'm sure. But next time you go to your landfill or your transfer station, go to the swap table, as we call it, and see if you see an old desktop PC. Bring it home, grab that power supply out. That's one of the best things you can get out of an old PC. I have 3 or 4 of them laying around. So you plug that into the wall. Of course, this is North America. If you have this can be set up to do 220 volts for the UK and Australia and other places around the world. And I don't have this. There's a schematic for this site. I haven't drawn the schematic yet. And I have code, but I'm not going to release the code out to anybody until I get this working, because the mathematics involved in controlling the blower, which we're going to get into, I haven't worked out completely yet. I got a few days before my parts come in. So you have a power supply that powers the Arduino and the blower. This blower works off of PWM, pulse width modulation, with a 5 volt signal, which is perfect because that's what the Arduino GUI has, PWM outputs, that I can control the speed of the motor directly from the GUI without any other internal logic. And then the Arduino, I keep saying GUI because I use that most often. The Arduino Uno is being used here. You can use a DUE as well. And I have 4 potentiometers, each going to the variable analog inputs, and I'm basically going to use these to control the volume of the air, the offset pressure, which could be 0, the respiration rate, and the symmetry, which I'll get into a few minutes. So you've got the power supply, the Arduino controlling the blower, and then basically have to make some adapters 3D printed, because you need to take this out daily and sanitize it, because bacteria will grow in any tube. Even if you have, if you put filtering on the input of the fan. And I plan to have a ionizer or a air purification system on the front end feeding this with a small humidifier, so I keep the warm, particle-free, warm, and moist, which seems to help with the coronavirus, the COVID-19 virus, or the China virus, as some people are calling it. So I have to make an adapter and a couple more adapters here. I haven't worked out actually. I believe that this exhaust tube that's going to go outside is going to be next to this, because I'm going to have a flap that goes between the two, so when the patient is inhaling, one flap door is closed to this, and then when he exhales, the fan will be off. That will allow the door to close and escape out the other tube. I just drew it like this for now. And this was a full-face snorkel mask that my wife actually found today on Walmart online, and it was $20. So we picked one of those up. It's got a little strap, and it's full face, which is nice, so you don't have to worry intubating anybody. You can just do this by putting it over your face. So the blower basically speeds up, blows air into the lungs, and then shuts off and allows the patient to exhale. And you can control those rates through these switches. So you should pause if you want to take a quick look at that. All right, now we're going to go on to the next slide. And forgive me, because I ordered a camera, which was coming from China of all places. It was cheap, and so I'm still waiting for that to come in. So I'm doing my presentations on my homemade little studio here. So this talks about the pattern. This is exhaling, and this is inhaling. So the blower turns on, pushes air into the lungs until you reach a certain volume, which I'm basically going to integrate that to figure out what the volume is based on your knob settings. And then it shuts off quickly and lets the patient exhale. This is why it's called a push release. It pushes air in and releases. If I had a fan or used two different fans, it could be an actually push-pull, where you push air into the lungs and then pull it out. This would be for someone, this could be for someone who's like, who can't breathe on their own. Of course, I'm not saying for anyone to build this. This is just what I'm doing, because this is not medically proven. It doesn't have all the safeguards that a medical device would be. It's the same principles, but it's for $130. You can't go wrong. I'd rather try something like this than die, personally. So that's why I'm coming up with my own, because these things around the world are getting harder and harder to find. And I'm actually thinking about making my own defibrillator. Now that's something I don't want to try on myself, or anyone else. Hey, where's that cat? No, I'm just kidding. My cats are cool. So basically, we can control the volume of air. We can control the respiration rate. I got 30. These are probably not the right values, but I'm just putting down values. And offset, which gives us positive pressure, which means there's always air going. The fan never really shuts off completely. There's always positive pressure. There could be, if you want to use this as a CPAP or whatever, and you can shut off the fan. So I have up to 10% offset availability through the knobs. And these are the ranges that I just came up with for the time being. These are probably going to change. So as you can see, and then I can change the offset, the volume, the symmetry, which means that maybe I want the inhaling to be more than the exhaling to be longer than the inhaling. I can vary this slightly. And eventually I'm thinking about making patterns, right? This is what we call a sinusoid, or a sinus pattern of breathing, which is pretty normal. But I may be able to do some math, and with another potentiometer, another analog input, I can make the breathing more linear or more acute, like a square wave. And there may be cases clinically that might help. I'm not a doctor, I'm an electrical engineer, so I invite any doctors that are familiar with this stuff to give me some pointers on it. Again, I'm not telling anyone to build this. I'm just sharing free information on the event that this may save someone's life. But again, nothing beats having a real respirator and trained professionals to help you do it. This is for me and me alone. I'm just sharing you what I did. And the last page I want to share with you is a 3D printer. I never bought a 3D printer. I wanted to get a 5-color one, and they were getting kind of expensive. So I'm holding off for a few years, waiting for 3D printers to be sold in every corner store, so to speak. But I have a friend who's going to print this up for me, and I'm going to draw it up on a mechanical drawing, and he's going to input it into his CAD system, and he's going to 3D print these up for me. So I got the basic dimensions. I want to wait for the parts to actually come in and make my own measurements. Sometimes data sheets aren't always accurate, and there's changes, so I want to make sure, because I don't want them to print out things and throw them away. As you know, 3D printing is a machine that'll actually build this up in layers over time, and it takes quite a while, and some of the plastic it uses can be expensive. And plus his time, he's a friend of mine, so I want to pay him for that. So that is basically this whole idea in a nutshell. Again, you should pause on any one of the screens that you would like to see. And feel free to write to me with comments, if any, but I don't have the code yet, and I don't have a schematic. But if you're an electrical engineer and you pull out the data sheet on this blower, and you know your Arduino, you could pretty much figure out how to wire this up. Again, thank you for your time.